Hi everyone, let's look at the HL component, electrochemical cells. Now when two half cells are connected, in the case of a Daniell cell, there's going to be movement of electrons. And we've seen that electrons are going to move from the anode to the cathode. So from the more reactive metal to the less reactive metal. So it's going to go in this direction. One of the metals which is more reactive is going to undergo oxidation, and the one that is less reactive is going to undergo reduction. The difference in tendencies to undergo oxidation or reduction creates a potential difference, and this potential difference is known as the EMF, the electromotive force, and this is going to drive the flow of electrons, and this is also known as the cell potential. Now, it's not possible to find the cell potential of a single cell, because in order to find it, you will need to connect it to some wires, and as soon as you dip a wire of another metal into, let's say, this half cell, if you dip another metal into this, it's eventually going to cause a potential difference. So what we do, we then measure the electrode potential of one half cell compared to another half cell. And the half cell used as a standard is the hydrogen electrode. So this is the standard hydrogen electrode, which is used to compare cell potential of half cells. Now, what is the standard hydrogen electrode? It consists of an inner platinum electrode. Let's see this. So you have an inner platinum electrode here, and to this you have hydrogen gas, which is going to be bubbled at 298 K and 100 kilopascal, and this is going to be in a solution of H plus ions at 1 mole per dm cube, and you have a porous spot which allows hydrogen gas to escape. So you have hydrogen gas in equilibrium with hydrogen ions, H plus ions in equilibrium with H2 gas. So this is the standard hydrogen electrode, which can be connected to any other half cell to find the cell potential of any other metal. So these conditions, you should know them. You should also know the concentration and these. This is the definition of standard electrode potential. So standard electrode potential of any half cell is the potential of the reduction half equation under standard conditions. So you have to know the standard conditions measured relative to the standard hydrogen electrode. So if you want to find the standard electrode potential of zinc, you're going to connect a half cell containing zinc solid and Zn2 plus ions at a concentration of 1 mole per dm cube. You're going to connect this to the standard hydrogen electrode here, where you have hydrogen gas in equilibrium with H plus ions at 1 mole per dm cube concentration. And the voltage that you get, this is going to be the standard electrode potential of zinc. So this can be found as minus 76 volts. So the conditions, so you have temperature 298 K, concentration 1 mole per dm cube of ions on both sides, gas pressure 100 kilopascal, and you have a salt bridge which is filled with potassium chloride solution. Now, in the data booklet, you will find the standard electrode potential of a list of reduction processes. By default, we always write the electrode potential as a reduction reaction. So the inert values are going to be given for reduction reactions, where the electrons are on the left hand side. So here you have the standard hydrogen potential, which is 0. Now if you look at the inert values, the more positive the inner values, the greater it has tendency to undergo reduction, and the more negative its value, the greater it has tendency to undergo oxidation. Normally in the voltaic cell, the more reactive metal undergoes oxidation, and this is going to be the anode. So at the anode you have oxidation, which means that there is tendency to lose electrons. The less reactive metal is going to undergo reduction. This is going to be the cathode, which means that there's going to be more tendency to gain electrons. So the more positive inert values means that they have greater tendency to undergo reduction, which means that they're going to be better at being the cathode. They will have greater tendency at being the cathode. So if it has more positive electrode potential, it's going to be the cathode. If it has less positive or more negative inert values, so more negative inert values, it means that it's going to have greater tendency to lose electrons, means it's going to have greater tendency to undergo oxidation. So these ones, they will have greater tendency to be the anode, and these ones will have greater tendency to be the cathode. When two half cells are connected together, electrons flows from the anode to the cathode. This we have already seen before. It's always from the anode to the cathode because the anode produces electrons. It produces electrons because it's undergoing oxidation, and the cathode is going to absorb or gain electrons, and gain electrons, it's reduction. Now the cell potential is the difference between the potential of oxidation and the potential of reduction of these two cells operating together. So it's the potential difference between the anode and the cathode when the cell is operating. So under standard state conditions, you need concentration to be 1 mole per dm cube for the reactants. The pressure should be 100 kilopascal, so that we can use standard electrode potential values. In order to find the overall standard cell potential of two half cells connected together, we're going to use the expression where standard electrode potential, the overall electrode potential, is going to be equal to the difference between the electrode potential at the right hand side minus electrode potential on the left hand side. So by convention, the right hand side is the cathode, and at the cathode you have reduction, and by convention the left hand side is the anode. Remember when we were drawing the cell diagrams, so you have the salt bridge and you have, let's say, zinc solid Zn2 plus in solution with Cu2 plus aqueous and then Cu solid. So this part, this is the left hand side. The left hand side is where oxidation takes place, and the right hand side by convention is where reduction takes place. So the overall standard cell potential can be calculated as the standard cell potential for reduction minus the standard cell potential for oxidation. So these values you can get them from the data booklet section 24. So you basically just need to find where reduction will take place, and the reduction will take place where you have the more positive inert value, and this one is going to be the more negative inert value. When you use this symbol, this means that you're measuring the cell potential at standard conditions, and the standard conditions is what you have here: 1 mole per dm cube concentration, 100 kilopascal pressure. So this is when you use the standard electrode potential. So this is the formula that you will have to remember to find the overall cell potential.